Let's start today's topic, Lagrange's equation for a linear harmonic oscillator, LHO. So I already did this, by the way, this topic, but my like in the screen recording it was not recording my voice, so I'm doing it again anyway. So fresh start. This time it should generally feel easy, and you know now understand where Lagrange's equation comes from. So this is just using a tool you trust. So we did the derivation of Lagrange's equation in some of our previous video, so we are going to use that equation as a tool in this. So what is a linear harmonic oscillator? Real life picture: imagine a mass attached to a spring lying on a frictionless table, free to slide left and right. If you haven't seen a spring, maybe you can think of it like, actually I have a picture. I already asked Claude for a picture. Let me show you. So this is what we are talking about. The spring attached, one side attached to the wall and the other side attached to a mass, but not using gravity. It's on a flat table. Okay, let's do it. So now we have a spring attached to a mass and attached to a mass lying on a frictionless table, free to slide left and right. If you pull the mass and let it go, it oscillates back and forth. The spring always pulls it back towards the center equilibrium position. This is the simplest oscillating system in linear harmonic oscillator, LHO. So setup is let x be the displacement of the mass from equilibrium. Mass equals m, spring constant is k, which is stiffness. Spring constant is stiffness. Bigger k, stiffer spring, the smaller x would be, right? Isn't it? Okay, so our goal is to find the equation of motion, how x changes with time, using Lagrange's equation. So recall the tool we are using. We are using this equation. We already derived it in another video, where L is equals T minus V, where T is this is kinetic energy minus potential energy for that spring we are going to use. So Q is generalized coordinate here. So Q dot is derivative of Q, time derivative of Q, right? Was it basically velocity? Anyway, so we are not re-deriving this today. We are just plugging a specific system into it. For our spring mass system, the natural choice of generalized coordinate is simply Q equals K. Q tha displacement, and in our case our displacement is x, displacement of mass from equilibrium. So Q is Q equals x, and to use this we need kinetic energy in terms of x and x dot, potential energy in terms of x, and we are going to plug those equation in our Lagrange's equation. So step 1 is to find kinetic energy. So kinetic energy का formula होता है half mv square. So half m and v square की जगह we have x dot square, since x dot is basically velocity, right? X dot is dx upon dt, is velocity, rate of change of displacement. So this is just a way of writing it anyways. Now potential energy, elastic P is stored in a spring stretched compressed by it. So this is the formula. By the way, मुझे भी नहीं पता था. I was thinking mgh, but mgh gravitational potential energy के लिए होता है. Now we have stored potential energy like elastic form, stretching और compression वाली. So उसके लिए ये formula है, which I didn't knew. मतलब I haven't studied this. आया होगा कभी 11th-12th में, मैंने तो पढ़ा नहीं है, whatever. So this is the formula we are going to use, and you need to memorize it or derive it from scratch, because I'm not going to anyways. So we are going to use the equation L equals T minus V. अब हमारे पास T भी है and V भी है. We are going to subtract those and apply Lagrange's equation piece by piece. Now to use Lagrange's equation we need to take we now have L, राइट हमने सब्सटीट्यूट करके एल निकाल लिया है. अब हमें एल का पार्शियल डिफरेंशिएशन लेना पड़ेगा क्यू डॉट के रिस्पेक्ट में एंड क्यू के रिस्पेक्ट में, एंड क्यू डॉट के साथ फिर हमें टाइम डेरिवेटिव भी लेना है उसका. सो दिस इज़ व्हाट वी आर गोइंग टू डू बेसिकली. सो वी आर गोइंग टू डू पार्शियल डिफरेंशिएशन विद रिस्पेक्ट टू एक्स डॉट, मीनिंग ट्रीट एक्स एज a fixed constant and differentiate L only with respect to x dot. Basically बस x dot वाली terms ही differentiate की जाएंगी, right? या वही differentiate की जाएगा, whatever. So here let's do it. अब इसमें x dot है ही नहीं इस term में. The second term has no x dot in it, so we are going to treat it as constant. तो इसका derivative होगा 0, so this is going to cancel out. This term differentiate with respect to x dot using power rule, bring power down and reduce by 1. So x dot बन जाएगा 2x dot, right? Then वो 2 cancel हो जाएगा and we are going to be left with this. I'll show you the maths part अभी आगे चल के. Just accept it for now if you don't know the maths part, क्योंकि मैं खुद भूल गई थी how to do the partial differentiation anyways. So we get this. Now ये इसका हमें टाइम डेरिवेटिव भी लेना है, राइट? We have the partial derivative. Now we are going to take time derivative, differentiate piece A with respect to time. अब mx डॉट का हम डिफरेंशिएशन ले रहे हैं. सो x का डिफरेंशिएशन लिया x डॉट, बेसिकली डिस्प्लेसमेंट का डिफरेंशिएशन वेलोसिटी का डेरिवेटिव whatever acceleration, right? So x double dot, I don't know how to pronounce it. So m is constant and derivative of x dot with respect to time is x double dot acceleration. So there is no math in it, or is it? I don't know. So now we have, हमने L निकाल लिया, उसके बाद उसका पार्शियल डिफरेंशिएशन x डॉट के रिस्पेक्ट में करके टाइम से भी डिफरेंशिएशन या डेरिवेटिव whatever करा लिया है. Now we have our value for this first term. Now we are going to do partial differentiation of L with respect to this x. So now x dot is going to be treated as constant, it's fixed. So x dot is, since x dot is fixed, तो ये वाली term अब 0 हो जाएगी, cancel हो जाएगी, right? Since it has no x, and this term is going to become x बन जाएगा 2x, k तो constant है ही, then 2 is going to cancel out. This is, we are going to be left with minus kx, and we are going to assemble like using Lagrange equation. We have mx dot for this part, mx double dot, sorry, whatever, minus of minus k. So mx double dot plus kx equals 0. This is our final result. This is equation of motion for LHO, the same equation that produces oscillating motion with the, I don't know about all this. So here is the summary if you want to see. Let me show you the maths part. So first of all, I told you कि मुझे लगा था ये mgh होगा या क्या चल रहा है. So this is the elastic potential energy, and you need, this is a standard formula that you might have learned in earlier physics. मैंने तो नहीं पढ़ा था because I didn't study anyways. So after this we have the maths part. So since you know the rule for differentiation is अगर xn होता है तो nx upon nx raised to n minus 1 हो जाता है, right? So x square becomes 2x. Similarly हमारे पास था ये अपना formula. Let me show you. Here you go. So m तो constant रहेगा हमारे केस में, m is not changing, only x and x dot are changing. So x dot की raised power 2 would become 2, x dot raised to power 2 minus 1, 2x dot leading, and then this 2 is going to cancel out and we are going to left with mx dot. Similarly we you can see the maths part, wait. And the second term would cancel out obviously, as you can see. अदर टर्म के साथ भी सिमिलर ही है. यहाँ पर we have x square, it becomes 2x, then 2 cancels out and we are left with this minus kx. So now the differentiating with time part. Lagrange's equation asks us to differentiate ask us to take d by dt of this. So m is just a fixed number, so it comes along for a ride. We need d upon dt of x dot, the rate of change of velocity, which is by definition acceleration. As you can see, no maths part, it is by definition acceleration. Putting it all together, we have this. I hope this is all clear. And that's it. There is nothing much in this topic. If you are interested in this spring potential energy formula and how it is derived, you can read this part or you may leave because this is not important. This is not exam relevant. But if you are interested, you can see. I'm just scrolling it slowly for you. You can pause and read if you want to. I don't think it is necessary actually, and I don't have that time. Yes, so this is it, and that's it. I don't think we have anything else in this.